Our goal in this video is to finish off the remaining topics in programs with multiple processes and interprocess communication. So that will bring us to an end of the current unit, and then in the subsequent videos we will start talking about the last unit, which is the IO subsystem. Alright, so let's get started here. Recall, towards the end of the last class we started talking about programs with multiple processes. So we said that executing programs can create new processes. Essentially, the process that creates new processes is known as the parent process, and these newly created processes are known as children of the parent process. The child processes may in turn go on to create new children of their own. So essentially, in an operating system we can have a tree of processes where processes have this parent-child relationships between them. Recall that we talked about these examples and definitions of daemons and applications. So I'm not going to go into these details again. This is just for your review. So we also went over this example Linux process tree in the last class. After that, we discussed three key implementation choices that operating systems face while implementing child processes. The first choice is with respect to execution of the parent and the child processes. So there are two possibilities here. The first possibility is that whenever a process creates a new child process, both the parent and the child processes can continue running concurrently in parallel. So essentially the parent process doesn't have to stop if a new child process is created. However, the second possibility here is that once a child process is created, the parent process must wait for the child process until it terminates. The second choice is with respect to the address space. Once again, there are two possibilities here. The first possibility is that whenever a new child process is created, it is simply a duplicate of the parent. So for example, the child process will have exactly the same code as the parent process. As opposed to this, again, the second possibility is that the child process has a different program. It has different code loaded into it. The third key decision or choice is with respect to resource sharing. Here again, there are several possibilities. Whenever a new child process is created, the question is whether the child process should get all of the a share of all of the parents resources, basically access to all of the parent resources, or maybe the child process gets access to a subset, a smaller subset of the parents resources, or maybe the child does not get access to any of the parent resources, and we instead provide separate mechanisms for resource sharing whenever the parent and the child processes need to collaborate. A key thing to realize about resource sharing is that whenever a new child process is created, the child process will need certain resources. For example, the CPU time, the memory, the maybe files in the file system, and so forth, to accomplish its task, to do its work. Now, a child process, there are at least two possibilities here. First is the child process may be able to obtain its resources directly from the operating system, or the second possibility is that it is constrained to use a subset of the resources from the parent process. Now there are pros and cons to both of these approaches. In fact, there are pros and cons to all of these decisions that we have in among the three choices. So for instance, if the child processes are always restricted to using a subset of the parent's resources, then the advantage of doing that is no one process can overload the system by creating too many child processes. However, the downside of this is if a process is creating child processes to for parallelism, to divide a certain task among several parallel concurrent processes, creating several child processes in this case can slow down the execution of parent process and also all the child processes, because they are restricted to just the parents resources. Alright, so in this video we will see what choices do Linux based operating systems make with respect to these three key decisions. In the Linux operating system, fork system calls are used for creating new child processes. So whenever an executing process wants to create a new child process, it will simply invoke this fork system call, which will then create a new child process for the executing process. Now this child process, once created, is a new process, just like any other process. So it will have its own unique process ID. It will have its own process control block in the ready queue. It would be scheduled by the CPU scheduler like any other process in the ready queue, and so forth. In the Linux operating system, by default, the child process runs concurrently with the parent process. So once the child process has been created, both the parent as well as the child process can continue running in parallel concurrently. So there is no requirement for the parent process to wait for the child process by default. It's not necessary. So if the hardware has true parallelism, for example, it has multiple cores, it is possible that the parent and the child processes can be scheduled on two different cores in parallel simultaneously. However, optionally, if the parent really wants to wait for the child to finish for some reason, then it can make use of this wait system call. So by invoking the wait system call, the parent's execution would be suspended. The parent would be moved to a wait queue, the suitable wait queue, where it would wait for the termination of its child process before proceeding further. So here is some more information about the fork system call. It does not take any parameters, and it returns a PID underscore T type, which is basically the process ID of the newly created process. PID underscore T is essentially a signed integer. However, this PID underscore T is used instead of integer for code portability purposes. So let's take a look at a simple sample code using fork to understand this further. So let's assume we have the code for a parent process over here, and it looks like this. So here is the code for the parent process. This is not a complete program, but this should do the job. So we have declared a PID variable, which is to store the process ID of the newly created process, and then at some point in the program we make call to the fork system call and store the return value in this PID variable. And after the fork, we have this print statement. We want to print created on the screen. So when the program reaches this point in its execution, the line that contains fork, at this after the execution of this system call, a new child process would be created. And given this is the code of the parent, the child process would look something like this. So essentially, as you can see, the child is an exact copy of the parent process. They both have the same code. However, after creation, the child process does not start executing from the beginning. So it won't start over. So essentially, the child process was created as a result of this fork system call. So after the execution of this fork system call, both the child as well as the parent will start executing from the line immediately after this fork system call, which is basically this line, cout. So the parent will execute the cout and the child will also execute this cout statement following the fork statement. Another thing you should realize about the execution of parent and child process is that once the child process is created, there is no guarantee about the ordering in which these two processes are executed. So essentially, the child process is an independent process. Both parent and child can execute concurrently. So immediately after the child is created, whether the parent gets to execute next or the child gets to execute next is determined solely by the CPU scheduling algorithm or the CPU scheduler. We cannot make any assumptions about that. So essentially, we don't know whether the created that we'll see on the screen is coming would be coming first from the parent or first from the child. All right, so let's talk some more about the fork system call. On the previous slide, we saw that the child process created using the fork system call is an exact copy of the parent process. So what that means is the child process will have all the variables, all the data structures that the parent process has. However, it is important to realize that these variables and data structures present in the child process, these are copies of the original variables and data structures in the parent process. They are not exactly the same. So if we look at the memory representation or memory allocation of the parent and the child processes, we'll find that both the parent and the child processes have different memory address spaces allocated to them. So let's assume this is the main memory, and this top bubble, circle over here represents the memory addresses allocated to the parent process, and this bottom bubble, this represents the memory addresses allocated to the child process. So continuing the example of the previous slide, if the parent had a variable PID, the child will also have a variable PID. But note that this PID is inside the parent's memory address space and this PID is inside the child's memory address space. These are two separate copies of the variable PID inside the main memory. They are not the same. So they both can have different values. So for the sake of this example, let's assume that the parent process has a process ID of 100 and the child process has a process ID of 200, right? So these are process IDs. When the fork system call is used for creating a child process, it actually returns two separate values to the parent and the child processes. So in this case, for instance, when this child process is created, the PID variable inside the child process would be set to 0 by the fork system call. However, the PID value, the process ID inside the parent process would receive the actual process ID of the child, which is 200 in this case. So essentially, the return value of the fork can be used to distinguish between the parent and the child processes at the runtime. So how can that be useful? So let's take a very simple example to understand that. So here is an extension of the code from the previous slide. When this fork system call creates a new child process, both the child and the parent will have exactly the same code as shown here. However, like we have seen, the PID value that is received by the child process from the fork system call is equal to 0. And the PID value that is received by the parent process is actually the process ID of the newly created child, which is a positive integer greater than 0. So we can use this fact to distinguish the child process and the parent process at the runtime. So basically what we are doing here in this code is we are checking the value of PID. So whenever the child process runs, it will find that its PID is 0. So we can use that to have a separate logic for the child process. However, if the PID detected is greater than 0, it's a positive integer, then we know that it's the parent process that is running, so we can have a different logic for the parent process. Also, in case the fork system call fails, then it returns a negative value, right? So that is what this last else is. So if there was an error, for some reason, let's say the fork system call fails to create the child process, then it will return a negative value for this PID that we can use to detect the error and print some error message and maybe terminate the program. So when the child process is created, it's first created, it is an identical copy of the parent process. However, it is also possible for the child process to execute a completely different program than the parent process. Now the way it is that can be accomplished in this code is, for example, if we replace this cout statement with an exec system call, and inside this system call we need to specify the program that we want this child process to run. So for example, if we want this child process to become a paint program, then we just specify the complete path of the binary of that program, and on execution of this exec system call, the memory address space of the child process would be completely replaced or basically loaded with the image of that paint executable binary. So after executing this exec system call, the child process would be a paint process. It will no longer be the same as the parent process. So that can also be done using the fork system call. We can create completely new programs or processes basically. So I have some more examples on the subsequent slides to illustrate this point further. So we have talked about the exec system calls on the previous slide, and we have seen how the child process can execute a completely different program than the parent process using these system calls. Regarding resource sharing, for most part in Linux operating systems, the resources are not shared. Now there are some caveats to this. So if the parent process has some files open in the file subsystem, the child process will get the file descriptors of these files. However, most other resources are not shared. The child process gets the resources it needs from the operating system. If the parent and the child process need to collaborate on a certain task, let's say they need to communicate with each other, they can do that by using separate interprocess communication mechanisms. These mechanisms are pretty generic, and they allow not only the parent and child processes to communicate, but any two processes can communicate in the operating system using these mechanisms. We will talk briefly about some of these towards the end of this video. This picture over here illustrates one possible execution flow of a parent and child processes after the fork system call. Now this particular example assumes that the parent will wait for the child to finish before continuing. The top branch here represents the parent's execution flow, and the bottom branch represents the child flow. So essentially what we see here is the parent was executing here, so there was just one parent process before the fork system call. Once the fork is executed, we now have the parent process which is separate from the child process. And note that both the parent and the child processes can continue executing concurrently. So immediately after executing fork, the parent process makes the wait system call. So it will now wait for the child process to finish before resuming and continuing its execution. On the other hand, the child, it invokes the exec system call. So essentially the child loads the execution binary of a different program into its memory address space. After this exec system call, the child process will no longer be the same or identical as the parent process. So after the exec system call, the child executes for some time, it does the necessary tasks, and when it is done, it invokes the exit system call to terminate. When the child terminates, the waiting parent process is intimated, and now the parent process resumes its execution from this point onward. Next, let's walk through some code examples to further understand the workings of the fork system call. This is the simplest example that we will see. So here we have a very simple main function. Here we have defined an integer PID to store the return value of the fork system call over here. So in this code, our PID is a parameter to the switch case statement. So if you have worked with these statements in C++, you would know that inside this switch statement, this case 0 is basically equivalent to saying if PID is equal to 0. So that would basically mean that this is the child process. Recall that the fork returns a 0 to the child process. So inside the child process, we want to print I am the child, and then break out of the switch case statement. That this default case is basically equivalent to saying if PID is greater than 0. So which is basically indicating it's the parent process. So the parent process basically would print I am the parent of, and here it would print the process ID of its child process, right? So for example, let's say the process ID of the child is 1 2 3 4 5. I'm making this up. And then after printing this statement, it will break out of the switch case statement. And finally, this case -1 is basically if PID was negative. So essentially, if fork had some error, it maybe could not create a new child process. So you'll print some error message and exit the program. So this is a very simple process. Feel free to execute this on the CS1 server. The goal of executing this process is to realize two things. So one is that both the parent and the child processes, they will run concurrently. And the other important thing to realize is if you run this program multiple times, excuse me, so if you run this program multiple times, you will find that these two statements, I'm the child, and the second statement, I'm the parent of this process ID, they can print in different orders. So sometimes the child statement will print first and sometimes the parent's statement will print first. Essentially, the order in which these statements appear depends on the order in which the CPU scheduler schedules the two processes after the fork system call executes. The second example over here is also very similar to several examples that we have seen on the previous slides, but the goal of this particular example is to illustrate the use of the exec system call and the wait system call. So once again we have this parent process executing, which makes a call to fork, creates a new child process, and then we have this similar if else conditions. If PID, this the process ID that is returned by the fork, if it is negative, then that indicates an error. If the PID is equal to 0, then we have a child process. So we are inside the child process, and note that in this case the child process is executing, it's making a call to the exec LP system call. Now this exec LP is basically a variant of the exec system call mentioned earlier in this video. So originally when the child process is created, its memory address space would be identical to this parent process. However, after executing this exec LP system call here, the memory address space of the child process would be replaced by the program binary whose path is listed over here. So essentially in this example, we want to replace the child process using the program binary of the Unix list command ls. So you would know that this ls command is used to list the contents of a certain directory. So it will, if you execute ls inside any directory, it will print the list of all the files and subdirectories present inside that directory. So after this point, the child process would no longer be the same as the parent process. It would actually behave as the list utility. Finally, this last else is basically if it corresponds to a PID value that is greater than 0, a positive PID value. So that's basically the parent process. In this case, the parent process is invoking the wait system call with a null parameter. So what that means is the parent process will wait for the termination of its child process before moving any further from this line of code. So the parent process would be moved to a appropriate wait queue. Whenever this child process finishes, the parent process would be revoked. It will be re-invoked and it will start execution from the line immediately following this wait system call, which is basically the cout in this case. So once the child process terminates, the parent process would print child is complete and then the program would terminate. Alright, so let's talk about the third and final example, code example for this fork system call. So once again we are using fork to create a new child process. Note that the parent process has an integer counter variable which is initialized to 0. This is the code for the child process and here is the code for the parent process. So essentially in the child process we have this for loop that runs from 0 to 4, so it runs 5 times, and inside this for loop we are printing child process counter equal to plus plus counter. So we'll print the current value of the counter and increment the counter by 1, and exactly the same thing is happening inside the parent process as well. So the only difference mainly here is in the parent process we say parent process and counter equal to plus plus counter. So the question here is, if you run this program, what output would you see? Now before listening to my explanation, you should pause the video over here and think for yourself. The main thing to figure out here is since both the child and the parent process are incrementing the value of variable counter, would you see something like this? Let's say you have a print from child process saying the counter value is 1, then the parent process says counter value is 2, then the child process says the counter value is 3, then the parent process says counter value is 4, and so on up to all the way to counter value of 10. Now this is one possibility. So essentially, if the child process and parent process, they're both incrementing the counter value, and if one of them has incremented it from 1 to 2, the next time it is incremented it changes to 3 for the next, even if it's a different process, then to 4, and so on up all the way to 10. That's one possibility. The other possibility is something like this. Let's say you have child process saying the counter value is 1, then the parent process again, when it increments, it says the counter value is 1, then the child process says the counter value is 2, then the parent process says again 2, and so on all the way to child process saying a counter value of 5 and parent process saying a counter value of 5. I'm hoping that you paused the video and thought enough about this. So let me now give you the answer. Recall, we have seen that the child process will be a copy of the parent process. So it will also get a copy of all the variables that are present in the parent process. However, these variables would be copy of the original variables in the parent process. They are not the same variables. They will have the same name, but they would have different allocations in the memory. So essentially, the counter that the child process is incrementing is separately allocated from the counter variable that the parent process is incrementing. So these two are different counter variables. So when you run this program, you will not see something like this. You will see something like the second possibility. When the child process prints, or you will see value of counter going from 1 to 3 and all the way to 5. And for the prints of the parent process, again you will see the value of the counter going from 1 to 3 all the way to 5. Okay. Now it is important to realize that the messages coming from the child process and the parent process may not be interleaved exactly as I have shown over here. The interleaving would depend on how exactly these processes are scheduled by the CPU scheduler. I encourage all of you to run this program on CS1 and see for yourself. Also try executing the program by commenting out these sleep statements. You would likely see various interleavings of these print messages. Now here is another kind of question that you may see on the exam. So the question is asking, here is the code for the parent process, and note that there are two fork statements inside this parent process. So the question is asking, if we run this program, how many processes are created by this program, including the initial parent process. So let's think about this. So I'm going to draw a process tree corresponding to this process. So let's assume that this parent process, the code for which is shown over here, is this process P0 at the root over here. Now inside this parent process, there are two fork statements. So corresponding to each fork statement, a new process would be created. So because there are two fork statements, this parent process will have two child processes, P1 and P2. So let's assume that P1 was created by this first fork statement and P2 was created by the second fork statement. So after creation, when P1 starts executing, it will start executing from this next fork statement over here. So P1 will actually execute one fork statement, so it will have one child. So let's say P3. However, when this P2 starts executing, so P2 was created by this second fork statement over here. So P2 will start executing after this fork, and there is no other fork statements in this program. So P2 will not create any additional childs. So in all, including the original parent process, this program will create 4 processes. So that brings us to an end of programs with multiple processes, and now we are ready to dive into the final topic of this unit, which is interprocess communication. Let's start with some background here. There are two types of processes. So there are independent processes and cooperating processes. So an independent process is basically the one that does not share any data with any other process in the system during its execution. As opposed to that, a cooperating process is the one uh, which does share data with other processes in the system. In other words, a process is said to be cooperating if it can influence or be influenced by other executing processes in the system. So with those definitions, an obvious next question is, why do we need cooperating processes? The important reasons are listed over here. The first is information sharing. It is possible that several executing applications or processes are interested in the same piece of information. So if so, we must provide an environment that allows concurrent access to such information and such data. So another reason for cooperating processes is computation speed up. So imagine that we have a task. It's a enormous task and we want to make it run faster. So one way of doing that is by breaking it into several smaller subtasks, such that each of these smaller subtasks, can execute in parallel with each other. Now these smaller subtasks, because they are basically working on the same task, it is possible that these subtasks may need to sometimes collaborate or exchange information, share data with each other. So that would also require some cooperation between these subtasks or processes. And finally, we may need cooperating processes for modularity and convenience. So it is possible that we may want to construct a system in modular fashion so that it is easier to design, develop, debug, and maintain. So essentially, to build a modular system, we may want to divide it into divide the system functions into several separate processes or threads, and these several processes and threads may need to communicate with each other to provide the necessary services. So in order to communicate with each other, the cooperating processes need interprocess communication. There are two models of interprocess communication that we will talk about: shared memory and message passing. So let's start with shared memory. So let's first look at the basic idea here, right? So recall, let's say there are two processes A and B that want to communicate with each other. Now recall, by default, the operating systems do not allow a given process to read or write into memory address space of another process. Okay, so essentially, uh, if these two processes need to communicate, we need to establish some shared region in the memory where both these processes can read and write. So that's the basic idea. So once this region of memory that is shared by the cooperating processes is established, the processes can exchange information by reading and writing data into this shared region. That's the basic idea. Let's look at some specifics now. Let's assume that the process A and process B here, they want to communicate with each other. Let us further assume that this top rectangle, this represents the memory address space of process A, and this bottom rectangle from here to here, this represents the memory address space of process B. So if these two processes want to communicate, one of these two processes will need to create a shared memory region inside its address space. So let's assume the process B, it decides to let's say dedicate this portion of its memory here and create it as a shared memory region. Now the creation of this shared memory region can be done with the help of appropriate system calls. So once this shared memory region is created, any other process that wishes to communicate with process B through this shared memory segment will have to attach this segment to its own address space. Now from this point onwards, both processes can communicate by simply reading and writing into this shared memory segment. Now there are a few important things to note here. Communication using shared memory is typically pretty fast. So initially, when this shared memory region is being established, this requires use of system calls. So using system calls is relatively slow. However, once this shared memory region has been established, After that, any accesses to this shared memory region, they are normal memory accesses. They are not system calls. So these normal memory accesses are pretty fast. The other important thing you should note here is once this shared memory region has been established, the kernel is no longer involved with the communication, with the inter-process communication here. The two cooperating processes, A and B in this case, they are responsible for deciding the data that they exchange via this shared memory region. So that was shared memory. Now another way the two cooperating processes can communicate with each other is what is known as message passing. So message passing basically provides a mechanism for cooperating processes to communicate without sharing the same address space. Now this mode of communication is especially useful if let's say the communicating processes are executing on two different physical machines. They are not on the same machine. They are not sitting in the same physical RAM. And let's say these two cooperating or communicating processes, they are connected over the network. Let's say the internet. So something like this. Let's assume this is our computer 1 over here, and this is computer 2, and process P1 is running inside computer 1, P2 is inside computer 2, and these two computers are connected with each other over some network, let's say the internet. So in this setting, these two processes, they are clearly not in the same RAM. Here in this situation, establishing a shared region of memory to communicate with each other is tedious. So message passing is a more convenient form of communication in such situations. So in message passing, the communicating processes, they typically communicate by using two system calls. So whenever a process needs to send some message to another process, it will use the send system call. So the message that needs to be sent would be passed as a parameter, and similarly the process that wants to receive certain message, it will use the receive system call, and again the message is the parameter here. Now this parameter message that is passed in the send and receive system calls, this could either be fixed size or it could be variable size. These are all implementation dependent details which are beyond the scope of this particular discussion. However, for simplicity and for illustration purposes, let's assume there are two cooperating processes, process A and process B, that are sitting on the same machine, same physical machine, and using let's say send and receive for inter-process communication. So whenever process A wants to send some message to process B, it will invoke the send system call, and this message would then be stored in the kernel address space. When process B is ready to retrieve the message, it will invoke the receive system call, and then basically the message would be retrieved from the kernel address space and delivered to process B. So this is a very high level description of how the message passing would work. But an important thing to note here is in every exchange of message between process A and B, system calls are involved. So this form of message exchange is going to be slower as compared to the shared memory. Recall, in the shared memory, the system calls were involved only at the beginning for establishing the shared memory segment. After that, the reads and writes that are done to the shared memory segment are treated as normal memory accesses. They are not going through the kernel address space. Those are not system calls. That's why shared memory is faster as compared to message passing. However, a major advantage of message passing is that it extends very nicely to a distributed environment where processes are running on different computers. So something like what is shown over here. So in such an environment where processes are on different physical machines, it is very cumbersome and tedious to establish a shared memory model of communication. So here message passing is preferable. Finally, it is important to realize whenever there are cooperating processes, they need to have a predetermined, well-defined set of data exchange protocols in place. Now, it is important for these protocols to specify things like the format of data that will be exchanged, exactly when a process is going to read, when a process is going to write, or similarly when is it going to receive some data or send some data. So these details need to be predetermined, otherwise communication cannot take place effectively. So here is a very simple example. Let's assume there are two processes. Let's say we have a client process and we have a server process. Let's assume that these are client and server processes of a distributed game. So often or periodically during the game, as the game progresses, the client sends this information, right? So it will send, let's say, the player name and the current score of the player, this packet of information to the server. Now it is important that both the client and the server agree upon the format of this information. So for example, in this case here, I'm assuming that name and score, they are separated by a semicolon. And the other thing I'm assuming here is that in this string, let's assume this is a string that is sent, the name appears first and then the player score, okay, and not vice or not reverse. So note that obviously the server needs to know that this is the order in which information is going to be sent, otherwise it cannot decipher it. So similarly, there are other details like the client and server need to agree upon when exactly this information is going to be sent, so the server knows when to expect it, and so forth. So these are the details with which the operating system kernel is not concerned. It is the responsibility of the processes or the applications to determine these sets of rules. Alright, so I hope that helps clarify the need for these pieces of information over here. Finally, before closing our discussion, I would like to point out there are several other issues when dealing with shared memory and shared data variables in among cooperating processes. For example, synchronization that we haven't talked about. You would learn about these details in multi-threaded programming in the next course in the sequence, CPSC 5042. Similarly, you will also learn more about message passing in network programming over there. So I hope this was helpful. Please let me know if you have any questions. Thank you.